the work here is very different. You don't need an Einstein to solve this problem. Equation is 2, I showed you. You don't need a big people. You need that innovation, some understanding which will solve the problem. So is the problem description clear? You can have any more question. The one is your lab. What people went through to solve this problem. Next file, please. So I just give that example already. 90 minus 25 by 100, 0.65 C per watt, right? I was saying 125, but actually 90 degree. Junction can see only 90 degree. It's basically K theory 1 or some problem you had in high school. 0.65. Let's see what the numbers are in real life. We'll see it. We'll have a plot. So we need how much? 0.65 means you have a chip, you put it in, then you connect it, you put a plastic around it. Have you seen your diode? There is plastic around it. After all this thing you do, it should be 0.65. I'll give you the numbers. Next file, please. And next one, okay, believe me, as I just said, it's very hard to achieve that number. Very hard. I said 1 at that time, now it's 0.65. Next file. This is what you see. There's a chip right there, and then the chip is on the top. The heat can go out in many different directions. The chip is on the little thing that I/O, that the path is connected to. That's a chip. I/O means input-output connection. So heat can go out. Then there's a plastic around it. You see that in your life, plastic, like 747 diode op-amp, right? It's a plastic, but there's silicon inside. And the plastic and all this molded, everything is out. So this basically, the heat has to go from junction to case. You have a plastic on the top. First it has to come from junction to the top. Then from top you blow in air or something you do. That's an ambient. And some other connectivity may be there. So what is that? It's same thing. You have a water heater. It has to go to the metal. Then it has to hit the water. By the time the temperature here is 800, water temperature is only 100. Same thing. So this is very hot. Then it goes to the plastic, gets a little cool. Then you blow an air on the top of it, it gets a little more cooler. That's the ambient temperature outside. Let's look at this number. We're looking for 0.65. Let's do some measurement on those numbers. At that time when I started at Intel, what was the number during that time? Next file, please. The numbers are that theta j value that I said. Look, how much is the number? I need how much? What is the number? 40. I need how much? 0.65. It is 40. Is it possible? So temperature will be how much? 25, 40, 100 what? Equation, number 1 equation. 2000, it will melt. Silicon will what happen? Will melt. Understand the problem? So you looked at the number theta j1, you go to your boss and tell me, yeah, I know the number, and you know what? I think we could fix it. But landed up, theta j is 40. You multiply junction temperature, silicon will see how much temperature? 2000 degrees centigrade temperature, and it will melt. So it is not, this technology is not possible. So this is junction to case, whatever it is, you don't need to know detail. But the bottom line is, actually junction to ambient will be much higher. This is the case. Remember the picture? Because your water will be 100 degree, but outside will be 25 degree, right? Where you are having a tea outside, sitting, peacefully. Next file, please. So what? The reason why I got very popular around the world, during that time, even it's a 3 watt. Go back to the previous file, please. Even if the number is a 3 watt, multiply with 50, 120, it will be 150 degree. Agreed? Still it does not go to 90 to 120, even at 3 watt. During that time the CPU was people building at 32 megahertz is about, they are making this one about 3.5 to 4 watt. And when they first built the laptop was totally burnt. And this is where I took this project and I first built the laptop packages in 1989. And not even I built it, I eventually made it manufacturable to people to manufacture at a rate of 16 million units a month, not one unit. 16 millions around that time. And this is one of the, in 1990s it came out as one of the best discoveries in 1990s, around that time. One of them is CCD camera was. The one is to take a big camera, CCD camera. There are few of them, the list is there. I think I showed you guys. So that was built jointly with a company named Shinko, a big Japanese company. I also went to NEC, that's not the company, Nippon Electric Corporation, to build it, but they refused. But I eventually found people, convinced them to help me to build those, because Intel is not a package manufacturer. Understand? Intel builds silicon. Let's go to the next file. Let's show how I solved that problem from those concepts. So I built some package. These are all drawn by hand in those days. As my hand drawings. So you can see how hardworking I was to implement something. These are all patented process. So this is what the package 100 pin, 196 pin count packages I built. They call Goldwing lead frame. And this is the silicon chip. I wire bonded them. Silicon chip is about 0.5 mil, about 100 micron. So when I bonded them right near the plane, right here, is only 100 micron. The one I was talking about, the low resistance, remember? I solved the problem by putting a plane underneath there, and I bonded them to make sure the resistance is very low. So there may be hundreds of ground here, and all of them is 125 micron. They may be 0.01 divided by 196 600, so it will be 0.001 inch, 0.001 ohm times 100, nothing. It's very small drop. Next file. Basically what I did, I have the silicon at the middle where you see the wire bonded. You see this bonding right here? This is only very small, 5 micron, 5 mil, about 125 micron. The many of those is a square. So I keep bonding them down, resistance is almost zero. This is another plane which is little longer, and these are the lead that goes out to the I/O. You see, they connect to the input output port. I build this package. It's all done by hand for your information. So you cannot complain in your lab that I have to do a lot of work. And I learned from my school, in my lab in Presidency College, how to do those. Nobody taught me. Next, many years back, these pictures are next fall. So this is the way I manufactured the process. There's a 6 strips. So I have the metal strips, which has this lead, put a capped on tape here, tape A, insulator. I put this metal, I put this tape, I put this plane at the bottom. So bottom has a whole metal, right? Then you have a plastic. Then you have the plastic, then you have the metal. I put all of them underneath, and this process, I actually build it 6 per lead, 6 of them. So this is a stamped lead frame. These are about 4 mil, 100 micron pitch here. This lead is coming out. The one you're bonding. Go back to the previous one. You see this? The next one. This is one. There's a next one on the other side. The distance here, right here, is only 150 micron. So I built that lead frame stamped. The mechanical engineer, I worked with them, built something, I took the copper plate, I stamped it. Everything is out, the lead came out. And then I etched it to make it very small, very fine, and then I plated the tips. Plated. gold plated. That little tip. How I did it? Is insulator everywhere except a little exposed place. If you don't do it, copper is going to be what? Oxide. Then you cannot wire bond them. You don't hold, stick it. Next one. So this is what the process went through. 6 strips. That way there's a millions of strips I can 16 million. I can build 3 or 4 million of these per year. And it solved the whole Intel's problem. Go next one. So now look at what I did. This is the value, theta j, remember? 60 was too big number, 40. All I did, believe me, I basically built it right here at 25. Actually, I did better. I made the plate a little bit of thicker, the back plane. So the silicon is putting on that metal. This all copper. It takes the heat out and it spreads it. Right? If you have a little thing, if you put a copper plate on the top, a big copper plate, the heat will go out through the copper plate, right? And the temperature of the copper will be lower than the bottom of your oven. So this one, I made it close to 22 to 23. So multiply 23 times 3, 66 plus 25 is how much? Huh? So that made 386 products successful. You understand what I did? Before it was 50. Right? You multiply with 3, what? 120. Room temperature is 25. So 120 plus 145, it won't work. It has to be 90 to 120. But this is the only one at that time worked. And I become hero in the whole world. This is all I did, nothing else. It is no calculation, no hanky-panky stuff. It is simply working with level of intelligence to make sure it is manufacturable. Not like, but I also went to see the movie. It's not I didn't see. I see many good movies. Rain Man I saw around that time, many good movies. Kramers versus Kramers. So it didn't destroy my life. I enjoyed going out, eating. But you know what? At the end of the day, I'm back to the same place where I started with. That dedication you need. You just cannot simply run under your mother's lap to save yourself. You got to get out of the mode of that kind of problem, and you got to be honest and do your work that you want to do, and you'll get it. I have not done much. This is 2 my discoveries. I did this, then I did this. Actually, I did a little bit of more thicker. From the reliability, it went probably right here. So that was the first laptop people built using this technology. Now they have a small fan on the laptop. And this was Zenith and all other companies. Let's go to the next one. Now this is another problem. That you cannot make the whole thing have too much sound in a desktop computer. So if you look at it, if you have a 90 dB worth of sound or 80 dB, you can stay in that sound 1000 hours. After that your ear will go bad. This curve you can keep it in your pocket. And if you have a problem, you show it to anybody, including your director. Or at your home if anybody makes a sound, take that plot. If there's 140 dB sound, you can only go up to 0.01 minutes. After that, eventually you will get diff. What do you call it? Diff? Whatever hell it is you're going to be, you will not be hearing anything at all in your life. So this is another curve that every computer manufacturer has to worry about it. You just simply cannot run a disk which is going like at infinite speed and having everything fetched in and out, and then everybody cannot work after 5 years later. Right? Simple. So this is another problem. The people has generated many concepts, cancellation of the headphone. They build something where they take the noise, they inject the same different phase of noise, but it's very hard to do it with the white noise. So it was never been successful. But you can come up with something which cancels any sound. You capture the sound here and you build a unit automatically, some control circuit. Here miss you. I'm telling you, right? You could do that when you grow up. Hear it. So you analyze the sound here. Here you see, right? You see too? Yeah, that's right. So you could do it. So you build a chip which takes the signal, what is here, and then you build a signal out of phase and mix them and let the people hear it. So put the earphone, there will be no sound. You can keep working. And that will reduce the lifetime of the ear. You could build it actually. I don't know anybody did it or not, but this graph, see how nicely I created a project for you? Just for you. Do it. I'll be dead soon. You could do it. Easy. You go buy few analyzer and you build it. Next file. Now this is something power versus density curve. We'll talk about the meaning of it. We said our power and the area is about 1.7 watt per millimeter square because it's 300 watt and area is 0.3 by 0.3. So use a plot of, if you cool by air cool, then you can only get, if you air cool, high speed air, you can only cool up to 1.5 watt per millimeter square. You cannot cool below that. The problem still exists. You can take a big fan and blow on the top of it. It's going to be only, you can only pump in the silicon chip how much? 1.5 watt per millimeter square. So today we're pumping about 1.7 right here somewhere. So this is air cool. This is chip power density. As the chip is getting tighter, the technology is getting better, the power going up. Chip power going up, but I can cool that thing. You know what is the effect of that? Effect is another entrepreneurship. You could work on it, get billionaire. Why? Because Intel cannot increase the CPU speed more than 3 gigahertz for the last 20 years. From 2003, still 20 gigahertz. Why? Because as soon as the frequency goes up, this damn thing goes here. Right? More frequency, more power. Right? Then you can cool. This is the maximum you can cool. So they design every chip to make sure you don't exceed in the chip more than 1.5 watt per millimeter square. Does that make sense? So Intel in principle can give you a chip works at billion gigahertz, but he can't. Why? Because your damn thing is going to melt. So that's another research you can do. It's still questionable. EC, mechanical, anybody. Next one, please. Now let's look at what is the meaning of those power density. That little thing is pumping a power density right here, which is a nuclear reactor. So your lab has a nuclear reactor. The laptop is like a nuclear reactor. This is a nuclear reactor power. This is the hydrogen burning with oxygen. And this is the surface of the sun. Look at the scale. Here we are, Pentium. Now this is a Pentium 4. Now this is only 0.1 micron. Now we are 65 nanometer. Now we are here. We are right here close to the sun. So today the laptop you have in your lab, it has a power density more than sun. And people solving that problem. What they're doing? And you have an option. You do have an opportunity. So that opportunity is, can we make that graph, this graph, all these graphs you put together in your brain, can we make it a better solution space where you can still run at a higher speed? Every time you, and that's 3 watt. This is 3 gigahertz still. That frequency didn't go up. It's still 3 gigahertz. But Intel in principle can make how much? 100 gigahertz CPU. 100 gigahertz, how much frequency it will be, the power will be? 100 divided by 3 is 30. Now they are pumping 100, 3000 watt. How much watt? 3,000. More than 3000, 30,000 watt. 100 times 300, right? Whatever hell it is. You got my point? So you have an option to do a manufacturing work, and you can, and I'm pretty sure if you ever go to any company and if they ask you a question, If you can project your thought process, you will get a job. You'll get a job and you'll be able to do better for them, so you will bring more job in the country. And I'm glad that some of you are here, not that many, but it is sad that people like me in this country sitting here, they don't come and listen to the lecture. The whole school should be off listening to this lecture today. It is so powerful lecture I'm giving you today. I don't know whether you're comprehending or not, that how powerfully people have solved the problem by sacrificing the life of the wife, children, everybody, and worked on these fields. It's not easy. Don't think working at night, leaving children behind, wife is very happy. And they used to come sit in the lab with those men and women. And that's the United States. And they have a best life than anybody could have it. They work. That's the fundamental part of their life. Next one. This is the channel length I talked about, implant and all these stuffs. This is the way it is going. In 2020, it could go to, this is 10 nanometer. So it could probably go down to below 10 or 5 or 6 nanometers. So there's a lot of problem. There's a quantum effect. What is quantum effect? I think I don't know which class I said. You got a big wall here. Your father built it for you, or in them, let's say. Why? Because you are escaping from the house all the time. Right? Understand? What his father did, build a big wall.
I still escaped.
Huh?
I still escaped.
And all of a sudden, yes, all of a sudden you'll find one day his father found, he's happily on the other side smiling. And that's called quantum effect. It's called tunneling. And this tunneling got a Nobel Prize by, I think 1972, by Leo Isaka, on tunneling effect of a heterostructure for a tunnel diode. I think I taught in the class where the resistance become negative. I think I taught it. The resistance goes negative, and that become a fundamental way of making a high frequency signaling. And that was discovery done. So that tunneling is what will cause a problem, because your channel is so small, right? All of a sudden it will tunnel. Electron will keep going. You don't have to put any voltage. He'll do by himself. It depends on his will. Like if he wants to go across the, the big wall, he'll be right there. So that is not a physics. That physics will kill it, any CPU logic. Because you get a mixed signal, you get a bad signal, and then you have a problem. So now I'll go through a step by step. I don't know where if I look at the file, I'll figure it out. How people has done to solve these problems. Next file, please. So I showed the plot. This is where I was very active building the first laptop, somewhere here. I did work 89, laptop came out right here. This is where 386SX I worked on it to build the laptop using that package. So now they're going continuously. Next one. Next slide, please. Now this is the problem I talked about. This is a CPU that all of a sudden can pump a power, right? Going through all this power supply. Many connections. So this has a lot of resistance. So people has worked every day to massage every one of those components, every one of this connection, to make it the best and the lowest resistance and impedance. You need this one smaller, 1.6 picohenry. Remember the number. So all this should add up no more than 1.6 picohenry. And there's many ways they do it. I don't want to go through the circuit simulation. You learn over a period of time. You can manage all these parameters. You see there is a solution. You will find it out. You worked hard. You will find it out. Next fall, please. Well, let's go to the previous one. The CPU basically looks like this. In this side, inside there's a little silicon chip. This is 1 inch, okay? Is that clear? About 1.1 inch or 1.2 inch. So this is 0.1 inch silicon here. Then they put the metal on the top, right? And that metal take the heat out. You put a flow heat, And this is on the other side is this. You see all these capacitors here? They mount them. This is this connection. So when this guy wants a power, it comes from where? Here. It doesn't come from here. We put the power supply right here. So there are all these capacitor will deliver 100 amp instantaneously, but there's still a connection, right? This has to get connected to on this side in a small place. So these problems people also solved day in and day out. 3,000 engineers probably working to solve it. So this is the circuit. You could massage it and it could be hero. You can figure out how to do things. There's no big deal. You could make 1,000 amps here and see whether it's a solution or not. Next fall, please. Now this is the way general picture looks like. You cannot sit with your power supply on the top of a chip, as I said. So, but you still need 1.6 picohenry kind of number, right? So this is the die, silicon die. You see, this is silicon. You see this? These are called solder balls, discovered by IBM in 1962. They have a 150 micron pitch. So if you have a 0.3 inch, it's 300 times 25 is 12,500 micron divided by 150. So that array is all the connections, that many bumps. So this is a 0.3 inch by 0.3 inch, and they are populated in that 0.3 inch. Populated these bumps. So what they do, this is your package. This is called organic package. They take that die and flip it. You now think of it, there's a 3,000-4,000 bumps. How many? 3,000-4,000, I calculate area array, 150 micron divided by 0.3 inch, many bumps. How you know they're going to be all connected in the same place? And they're selling how many units? 80 million units. All 3,000 bump will never fail. Everyone will be connected. Understand? That process is also developed by IBM in 1962. It's a miracle how all 320,000 bumps is all going to be placed in the right place and happily sit together. They will not even melt. Have you tried to do solder? Yes. You connect it, goes to somewhere else. It never works right. You could try it. Sanchali, in the lab, try to solder it. This is, you see your hair, cut half. That's the spacing. Cut your hair half. That's the spacing. That spacing, they're building and flipping it, everything connected happily, your laptop working, everything working. Do you think it's an easy technology? Are you comprehending what I'm saying? And that's called entrepreneurship. That's called real innovation. It's not doing an Einstein equation all the time. That's a different innovation. Like I said, Apple making money, Einstein did something else, and this is something else. All three innovations I can talk about, but today I'm only talking about this innovation. So this is, these bumps, like your hair cut half, this pitch, and they're soldered. So there's so many bumps, this height is about 60 micron. 60 micron. You cut your hair how many times? 10 times. That height is this height. Or maybe whatever, 5 times, whatever you cut. They connected, and these capacitors are these ones. Remember I told you? So they supply the power immediately instead of coming from outside. And these are all complex technology to deliver the power to this guy. So you can see 1.6 picohenry number. And that is a $1 trillion technology. More budget than ever India has spent money to build these technologies from 1960s. It is not building a house and your price is going up because of the inflation. Dollar and rupees in my time was 77. Now it is 75, 10 times. Those money has no value, but this has a value. The technology will last.